Welcome everybody to the Tel Aviv seminar on computation, geometry, and robotics. We have with us today Dror Dayan, who will tell us about his MSc thesis results, the thesis that he defended successfully yesterday. When we go to high dimensions or to many degrees of freedom in robotics, and we want to implement the algorithms, many of the techniques in computational geometry are difficult to implement, and the robotics community has devised a parallel set of algorithms that are fairly easy to implement, and in recent years they also come with provable guarantees. Most of the guarantees for algorithms in motion in robotics hold when the number of samples tends to infinity. Dror's work is special in that it shows guarantees for multi-robot motion planning with only a finite number of samples. Dror, please.
Thank you very much, Dan. Hello, everyone. My name is Dror Dayan. I will be presenting our work, Near Optimal Multi-Robot Motion Planning with Finite Sampling. This is a joint work with my advisor, Dan Halperin, and Kirill Solovey and Marco Pavone from Stanford. Okay, so first, our motivation. There are many multi-robot systems today, and it is very likely that this will only grow. Current examples include manufacturing, warehouse robots, drone delivery systems, and space exploration. Via these examples, we can think of a few qualities we would like from our motion planning algorithm. First, we would like it to be complete, meaning if a path exists, it should find it. Second, we would like it to be near optimal, meaning it should find a path which is minimizing the cost, let's say the length of the trajectory. Other things we would like to be fast and scalable. And another thing which is sometimes overlooked is that we might want it to be reliable. And what I mean by reliable, I mean that the algorithm must surely finish within a finite time. Most random algorithms usually miss this quality because, well, they are random by nature. Okay. So as for the structure of this talk, I will start by defining the multi-robot motion planning problem and the common approach for solving it. I will then state our contribution. Afterwards, I will define relevant definition and state our theorems. Then I will give an overview of the proof. I will finish with experimental results and future work. If there are no questions, let's dive right in. Okay, so multi-robot motion planning is a fundamental problem in robotics where each robot needs to get from its start position to its goal without colliding with obstacles nor with other robots. We consider the problem in the continuous domain. There are other variants that consider the problem on discrete graphs. The core of our work is finding a good discretization and proving it. I will define what is good mathematically later. The figures on this slide are our test cases. In each figure, each robot is presented as a disk and a circle. The disk is the starting position and the circle is the goal. Now that we have established the problem, a common approach for solving it is sampling-based motion planning. In sampling-based motion planning, samples are taken and connected to create a discrete representation of the space. One of the common sampling-based algorithms is PRM, in which you sample points, remove the invalid points in the configuration space. I should specify that. We remove all the invalid points, and we connect each point to other close points if the linear path between them is valid. So, okay, now, of course, both the sample set and the connection radius has great implication on the final roadmap. Now, sampling is usually done in a random manner. but we will use a regular sampling scheme. I will describe it later. And as Danny said, PRM has asymptotically optimal variants, such as PRM star, which guarantees that a path will be found and it will be near optimal, but these guarantees are only for infinitely big sample sets. As for our contribution, so first, in the single robot case, we improve upon previous results by an exponential factor, exponential in the dimension. And due to the limited time, I will skim over the single robot case and mostly talk about the multi-robot results. Now, in the multi-robot case, we proved the first result on multi-robot motion planning with a finite sample set. And not only that, but our results are also near optimal. Our results can be used for near optimal motion planning within bounded time using any tensor roadmap algorithm. These include A star, DRT star, M star, and conflict-based search, which you may remember from Orange talk 2 weeks ago. Conflict-based search is considered to be the state of the art right now. And so this is nice. Now, the definition of the tensor roadmap will follow shortly. And another thing is that our result can also be used to show that no delta clear solution exists within a bounded time. And the animation here on the right is an animation of our solution for one of the test cases, but more on that later. Now, in order to mimic trajectories, we wish to have a sample set which produces a good coverage of the space. The general term for what we're looking for is epsilon cover. Now, as I said before, we will use the regular sampling distribution. We call it the staggered grid. It is comprised of 2 square grids of size length 2W, and so is very simple to produce in 2 dimensions. And the staggered grid can be seen as the first row. This is this set, and then another set of points.
Dror, the sound is not perfect, and I think a possible solution is that you will talk a little slower.
Yes, okay, definitely. So I hope you heard me so far, and I will try and speak slower for now. So again, the staggered grid is our sampling distribution, and it comprises of, it is a union of 2 point sets. The first one defined this way, and the second one defined this way. In 2 dimensions, it's easily seen over here. And its size is exponential in the dimension, and we know that as beta grows smaller or gets smaller, beta is the radius of each ball, we need more balls to cover the entire domain. Now, in a higher dimension, it's a bit more complex, since if we keep the idea of putting tangents balls as we did here, it will no longer produce a cover. So we also need to inflate all the balls. I will show you an example in 3D. And so in 3D, for example, you can see that if I only put balls which are tangent to each other, there is a hole here. It does not cover the entirety of the domain. And to fix that, we need to inflate all the balls, and then it will cover the domain. This is, of course, not the proof. The proof is in the paper. Okay, so let's continue. Okay, so I'll now describe an underlying structure in many multi-robot planners, the tensor roadmap. The tensor roadmap is one way to combine multiple single robot PRMs to a multi-robot graph, and is defined in the following manner. So for our robots, we denote by VIEI the PRM of the ith robot, and by G the tensor roadmap, where each vertex in V hat is a vector of R vertices, each from its robot's PRM, and an edge exists between 2 vertices if either all the robots stay put or if each robot either stays put or moves on an edge on his PRM. This graph is used sometimes implicitly by DRT, DRT star, config-based search, and so on. Let's look at an example. So, for example, here we have two graphs which are combined to the tensor roadmap over here. And let's look at these two vertices. There is a vertex which corresponds to that. And now, if we keep this robot still and move this robot on these two edges, we get these two edges on the tensor roadmap. If we do the other way around, meaning the first robot moves, but this robot stays still, so we get this edge. And if both robots moves at once, we get these two edges. Now, an important thing to note here is that not all edges in the tensor roadmap are valid, because robot-to-robot collisions are still possible. It is the responsibility of the planner which uses the tensor roadmap to check for these robot-to-robot collisions. Now, another thing we need is the concept of delta clearance. A trajectory is delta clear if the distance to the nearest obstacle at any time is at least delta. Okay, in the multi-robot case, other robots are also obstacles for that matter. Now, this is a very common requirement in the sampling-based approach because you need some volume to be able to sample in a region. Otherwise, you just cannot sample them. Okay, so next we wish to give a measure to the quality of a sample. And I promise it is not as daunting as it may appear, it is rather intuitive. So given R robots, a vector of R sample set, X, and a vector of R connection radii, R, we say that XR is epsilon delta complete for some stretch epsilon and clearance parameters delta. If for every delta clear motion planning problem, it holds that the length of the shortest valid trajectory from the start to the goal on the tensor roadmap is at most 1 plus epsilon times the optimal delta clear path. This is in the continuous domain, not on any graph. In other words, XR is epsilon delta complete if the tensor roadmap of the PRMs using XR encodes a valid path whose length is at most 1 plus epsilon times the length of the optimal delta clear solution for any motion planning problem, meaning this sample set needs to hold for any motion planning problem which I might throw at it. Let's look at an example. So in this example, we have this PRM, we have 16, I think, vertices and edges which connect it to a grid. And the cost of a robot trying to get from here to here on the continuous domain is, of course, 2 squared 2 of the length of one edge. But the cost, the optimal solution on the PRM here is 4 times the length of an edge because we cannot travel through the squares. So I left the definition here. We can see that it is not 0.1 delta complete because 3 times or 2 squared 2 times 1.1 is less than 4. But it might be epsilon equal 1 and delta complete for some delta. I don't wish to prove it, so it's a possibility. Okay, so unless there are questions on the definitions, I will continue to the theorems. Okay. So for the single robot motion planning, we proved the following. So for epsilon and delta, stretch and clearance, we define X to be a staggered grid whose size depend on epsilon and delta, and the connection radius to be this expression. And we prove that XR is epsilon delta complete, which gives us result which for very small epsilon delta improve previous result by this factor. And as I said, I will mostly talk about the multi-robot case, so let's go to this. Okay, so this leads us to the main theorem, multi-robot motion planning, epsilon delta completeness. Let epsilon be a stretch parameter and delta be a clearance vector. We define the sampling distribution X, where Xi is a staggered grid whose size depends on epsilon and delta. The exact dependency can be found on the paper. And the connection radii are, where Ri is this expression. And what we prove here is that setting X and R to these values guarantees that XR is epsilon delta complete. I also provide a table. So let's assume the configuration space is the unit cube and delta I is 0.1 for all the robots. As we can see here, for in 2 dimensions and with epsilon equals 1, we only need 1,201 points for each robot. What does it mean? It means that I'm guaranteed to have a solution which is at most twice as long as the optimal solution using only 1,201 points per robot. Okay, so let's look at an overview of the proof. So what we essentially want to do here is we want to look at some trajectory. It will be the optimal, and we are going to try and mimic it. So for each robot, we are first going to sample a lot of points using the staggered grid. And then we are going to try and say something like the robots are close enough to their collision-free trajectory at any time, so they are collision-free. So we, of course, going to have to do it mathematically, not by speech, but this is the main idea of the proof. Now, an important thing to note here is that we are talking about time. We wish to look at the location of each robot at any point of time, which leads us to the next definition, trajectory timing. So we wish to look at some points on the trajectory, which are of some distance, rho, away from each other. And we look at the time in which the robot will appear on the optimal solution. This will help us with the formulation of my previous statement. So as you can see here, we sample the optimal path, and we look at points on the path which are rho apart from each other. Okay, so now when we have that, what's next? So we need to connect this timing to our sample points somehow. So the next thing we are doing is we are connecting the staggered grid with the trajectory timing. We will need to find a point from our staggered grid which is close enough to each point in the trajectory timing. And as I said, we are having a cover, which means that I will have a point which is very close to any points in the domain. But another thing I'm going to need to show is that 2 consecutive points can be connected such that the whole edge is in the free space. So let's look at an example. So we are going to have 2 points on the optimal trajectory. Next to each point, we are going to have some point from the staggered grid. And what I also need to prove is that the whole edge between these 2 vertices is in the free space. We are going to use the clearance for that, of course. Okay, so if we look at it in the formal way, so it's this statement. So this is the formal statement which says that for any point in the trajectory timing, we have a point in the staggered grid which is very close. This is the first bullet. We extend that to all the points on the edge between 2 points of the staggered grid. The interesting part here is this bullet, which states that the whole edge is collision free. And we also have this last bullet here, which we are going to use to bound the near optimality. What do I mean by that? If we take beta and rho such that this expression is smaller than epsilon, then by definition, or because of this theorem, the length of our trajectory, which is this expression, will be smaller or equal to 1 plus epsilon times the length of the original trajectory. Note, I'm talking about the length of the trajectory. This work does not pertain to other measures of cost as for now. Now, for a single robot, we are basically done here. We only need to pick beta and rho. The exact numbers are in the paper. But for multiple robots, we still need something else. We need to make sure that the robots do not collide. Meaning we need to adjust the timing of the robots or something like that so that they will not collide. This coordination isn't easy, and that's exactly what we're going to do next. So we define this set of triplets where each robot, where the first item is the robot ID, the second is the timing, and the third is some vertex from the staggered grid. We sort this list by timestamps, and then we use this list to generate a sequence of composite vertices, meaning vertices in the tensor roadmap, in the following manner. Exactly one robot moves at each time, and this robot is the one whose timestamp is the one we're looking at right now. We go over all the items, and each time we go to the next vertex. Now, I must say that it is possible for multiple robots to move at the same time. It is just easier to prove the theorem with this subset of edges. Now, in the paper, we show that at any time, each robot is at most delta I divided by 2 away from its position on the delta clear path, and so we are done. Why are we done? Because the robots cannot collide, because they are delta clear. Now, we are doing this with the theorem I showed you previously with the many properties, and by setting beta and rho to specific values. Now, the way we proved it here is what caused the identical robot constraint. Okay, let's look at an example. So let's assume we have 2 robots, this robot here and this robot here, and they wish to go, or they need to get to their goals. So the first robot needs to get to here, and the second robot needs to get to here. And so the optimal trajectory is, of course, just to go on the straight line. But if they will both move at the same speed, they will collide. So there is some adjustment on the optimal trajectory to begin with. So let's assume the first robot got to this point at time 0.2, to this point at 0.4, 0.6, and so on. Let's see how it looks. So it looks something like this. The first robot moves a lot faster so that they will not collide. Okay, so another thing you can see here is I already left the points from the staggered grid over here. So let's assume we have this point, which corresponds to this timing, which is at most beta away from it, and so on. We have one point next to each vertex. So our solution, and again, I repeat, each robot will move alone. So there will not be movement of 2 robots together. We look something like this. Up to t equals 0.2, the first robot moves, and then this one moves, and again this one. Okay, and you get the point. We can carry on. We can look at it combined. So notice that I used different colors so that you can see all the robots moving together on the optimal trajectory and on our trajectory. So you can see that our robots are not so far behind, or are very close to the position of the robots in each time on the optimal trajectory.
Dror, can you please explain why you can do it?
Why can I do what?
Why can you do this coordination?
And I'm not sure I understand the question exactly.
You got two paths. How do you do the coordination?
So this is what we saw right here. And we sorted by timestamp, and then we looked at each timestamp and moved the robot which needs to move now. And by doing so, we made sure that at each point of time, each robot is exactly between the last timestamp on his trajectory timing and the next one, which we haven't got to yet. And by doing so, we made sure, let's go back to drawing, that at each time where this robot moves between these 2 points, the other robot will for sure be between this point and this point, because we haven't gotten to this timestamp yet. Okay, so the sorting we did before helps us here. Okay, so I hope that was clear. And I will jump to the experimental results. So as for experimental results, we used 4 test cases. And we use this test case is from Kirkpatrick's paper, which showed optimal trajectories for 2 disks in the absence of obstacles. So we have 2 robots. These are their destinations, and by Kirkpatrick's paper, we know that this is the optimal trajectories, or the optimal delta clear trajectory. We also have this test case in which there are 2 robots and a spiral barrier, and they need to switch places or almost switch places. Now, we use this test case to test how well we cut corners using the staggered grid. The original trajectory must keep some distance from the barrier because it is confined by the clearance, but we do not obey for that clearance in our trajectory. Now, in the 4 robot, the radius of each robot is 0.19, while the whole workspace is 0 to 1. Delta is 0.02, and this is our densest scene. And this scene here is our scene with the biggest amount of robots. We also used conflict-based search to solve this one, while all the others were solved using A star. And when I say solved, I mean going over the tensor road. Okay, so on the right, you can see the results. We look at the quality of our solution compared with the optimal delta clear solution, meaning we look at the cost of our trajectory, which is the sum of costs, divided by the cost of the optimal trajectory, which is again the sum of cost of each individual robot. And okay, so another thing here is the numbers. The numbers next to each data point are the number of PRM milestones for each robot. Now, notice that I'm talking about valid milestones, not milestones which were discarded. So you can see the difference in these 2 scenes are identical with regard to the number of robots and the size of the space, but the number of sample point of valid milestones is very different. Okay, so let's look at some results. So first, we can see that the pink line is better than the optimal delta clear solution for any epsilon, which is maybe a bit surprising at first sight, but again, our path or our trajectory does not have to be delta clear. So we can cut corners. And so this is specific, this is especially helpful in this scenario in which the delta clear solution must go all the way and we can cut the corners at each step of the way. So we outperform the delta clear optimal solution for any epsilon, which is very nice. Another thing we notice is there is a pretty big drop for small values of epsilon. And I think the reason for that is that the rapid increase in the number of sample points. What do I mean by that? We can see that the increase between epsilon equals 2 to epsilon equals 1.5 is almost 800 points, while the increase between epsilon equals 2.5 to 2 is only 300 points. And it is probably the rapid increase in the number of points which increased or decreased the length of our trajectory by so much. Okay, now another thing we can see is that the graphs are not monotone. You might expect that the smaller epsilon gets, the results should be better, but this is not mandatory because we are outperforming the theory by a large margin at any point. So there are cases in which we are just getting lucky with some sampling distribution when compared to another. For example, when epsilon is 50, we're probably cutting corners better here than when epsilon equals 20. In any case, for very small, we are keeping our guarantee that the trajectory will be at most 1 plus epsilons times the optimal trajectory. We can even say a lot more than that, that in all our test cases, we are only 7.5% worse than the optimal trajectory or the optimal delta clear trajectory, which is a lot better than anticipated. And another thing I can say here, notice that we do not have any results for all the cases where we have a lot of robots for size of epsilon. So you can see that there is a pretty big increase in the number of sample points for each robot, and there is some gap between what planners which use the tensor roadmap today are able to do when you have a lot of sample points, or they cannot do much. In A-star, it's obvious, but it's also happening in conflict-based search. When you have a lot of points in each robot's PRM, conflict-based search is having a hard time, and so we stopped when we had a few thousand points. We could not continue like in the two robot cases where we got to 60,000 points. Okay. Now, another thing we looked at is how well we did compared to random sampling. Now, the reason we did that is because you might say, well, it's very nice that you proved the theorem and we are guaranteed, but maybe in reality, if I just sample the random points with the same amount of sample points which you need for your staggered grid, I will still get results which are pretty similar. So as I'm going to show you, this is not the case. For example, if we look at the spiral scenario, we can see that if we use the exact same number of sample points, and we just uniformly pick random points, even the success rate is pretty low. So we ran the experiment 10 times. We picked random numbers or random sample points 10 different times. And when epsilon was infinity, we literally got no success, even for 25 and for 10. We only got reliable results for the spiral scenario when epsilon got really small in the area of 1.5 and 1. Now, even in the obstacle-free scenario, we still don't get 100% success rate for big epsilons. Now, the reason for that is probably that in some rare cases, there is two sides of the graph which cannot be combined because the connection radius is too small. So this is pretty encouraging. But let's look at the cost of the trajectory, not only if we succeed or not. So in the spiral scenario, we can see that we always outperform the random sampling. And also we can see that the random sampling converges to our result. We can see this in both scenarios. Now, this is not very surprising because we do know that PRM exists and that if you take an infinitely big amount or infinitely big set of sample points, you are guaranteed to find a solution which will be near optimal. So it's not surprising, but it is nice to see how big of a difference you get for big epsilons, meaning a small amount of points. In a small amount of points, you get really big improvement when you use the staggered grid compared with random sampling in both cases. Okay, let's head to future work. So the first thing in future work is our multi-robot results pertain to geometrically identical robots. The theory should hold for other cases as well, but clearance might need to be defined differently, and there is some work to do there. Next, the staggered grid is much better than the previous result, but still exponentially worse than the lower bound. We believe that better sampling schemes exist, so that's another interesting item. Next, a major problem while experimenting was the lack of fast algorithms for exploring a tensor roadmap. Some algorithms exist, but we were not able to use them for many robots. The example I gave was conflict-based search, which works well on small graphs, but when the PRM has a lot of sample points, conflict-based search does not scale that well. And lastly, more work can be done to experiment further with regular sampling, which seem to have great potential. Thank you very much.
Thank you, Dror. Other questions? Anybody? Questions? Dror, can you say something about the staggered grid in 2 dimensions versus 3 dimensions? What could further be done?
So let me get back to the slide. Okay, so the thing is, our goal is to find the best coverage using a set radius for each ball, because in the end we are going to get balls of some radius or spheres of some radius, and we need to cover the entirety of the domain. So in 2 dimensions, the staggered grid behaved well. What do I mean by that is that the balls fitted nicely, and there was some overlapping, but the distance between the center of the ball and the radius of the ball, or the radius was half the distance between 2 centers of the ball. Now, in higher dimensions, I said we need to inflate all balls, but it's actually the other way around. We actually squeeze the balls together because the radius of the ball is set, because we need the ball to be an epsilon cover. So we actually need to compress the balls together. So this is what I showed here. When I switched the radius to be a bigger radius. Now, you can actually see the exact relation right here. You can see that when the dimension grows larger, I need to compress the balls to be tighter together. This is the divided by square of b. Does that answer?
Yeah, I wanted to point out the fact that in 2 dimensions we can do slightly better. Perhaps you can expand on this?
Yes, so we do know that in 2 dimensions there is a better cover from like 50 years ago, which is done using triangles. Maybe I will find the paper for a second and show, or what?
No, you can just mention it. It's
Yeah.
some kind of a triangular grid.
Yeah, so there is some triangular grid which is better than the staggered grid. What I mean by better, uses less spheres to cover the domain, but it doesn't extend to the best of our knowledge. It doesn't extend to higher dimensions, while the staggered grid does, and it's actually very, very simple. I mean, you just take many numbers, just 2 grids. I mean, it's very, very simple. Where the distance between 2 balls is this, which is very, very direct and simple.